Hello, everyone. Today we're talking about quantum gravity. You probably think there is no such thing as a theory of quantum gravity because we haven't discovered it, but in fact, we know ways that things move quantumly. So it's not impossible to know how quantum gravity can work, does in fact work, and is not macroscopic. Although it is it is still built off of like the real question is the strong force and the stuff that, and we know that interaction, so we have that. But that's not what we're talking about. Like stuff happening with particles that makes them move about. And the answer is folding proteins and elastic or metallic bending, like elasticity type stuff. So, what happens on the atomic level when it comes to elastics and when it comes to certain metals and when it comes to protein folding is that the way that the molecular bonds form ends up making a certain structure and it wants to be in that. The ability of resistance with the way that the electrons are compared to the rest of the parts in the protein or in the lattice of the metal makes the crystals that they form and makes the bonds that they develop and the shape that it makes. So once you know that, and once you know that there's a certain type of way, and it all comes down to the just the bare reaches of its ability to deform, and how there's a limit to how much things will want to push, like a soap bubble's elasticity will only allow it to stretch so much and only allow it to sag so much, um, and it'll retain its shape, or it'll retain its normal relation to all the rest of the stuff that is connected to it, which is the rest of the soap bubble parts. That is quantum gravity, as well as a spring, or like I said, with folding proteins. The thing is that the structure itself has a certain amount of force that it can exert in one direction or another, and based on whatever compounds you're using, you'll end up with certain things wanting to move around and clump together. Normal gravity, on a macroscopic scale, is due to a large number of objects moving through space, all in similar direction, and as one hits another one, like anything hitting a carpet, it'll start to roll. So the moment you have um, so the type of stuff that would make planets form in the first place are one thing bumps into another thing, they all end up collecting and bumping and not letting go of all the other parts, so they clump together, whirl together, and end up eventually making planets, meteors, stars, gas giants. Um, but then, what actually makes the supposed gravity that holds something like a gas giant um, instead of allowing the gas to flow off into space? Well, the answer is the giant's not moving fast enough for that. If Jupiter was moving faster, that material would be flung out into space. Relative to everything else, the gas and everything is all being pushed sort of towards the giant in a regular direction. But because of its rotation, the push happens once, and then its inertia allows it to keep going with the giant. And then, as it turns, that inertia keeps on turning and refreshing with every rotation. So, like, if it starts spinning faster, the atmosphere will fly off. If it starts moving faster, the atmosphere will fly off. If it spins in the opposite direction or doesn't have any spin, the atmosphere will fly off. It's because the planets are spinning that you have an atmosphere. It's because the stars are spinning that it's able to hold itself together. And it's because it's moving through space. And normally just everything is already spinning. Once it becomes solid, like an asteroid or whatever, meteorite, it doesn't have to have that spin in order to do anything else. It's just solid. But so gravity isn't the fact that we're being pulled towards something. It's that something is moving towards us, and on the far side, we're not going away fast enough to fling off into outer space. Literally, if you launch from the front of the planet, it takes more effort than from the back of the planet. By which I mean relative to its motion through the solar system. So if the planet's moving that way through the solar system in that orbit around the sun, then the wake behind it is where you want to launch from, because then it doesn't take as much to get up and out of the planet. But we know this. We understand that. So it's a fraction of the amount of force necessary to launch yourself into space, but it is like time of day dependent. It is position of you in the solar system dependent, and it could make things a lot easier. I'm pretty sure they already compensate for it. So gravity really is other stuff clumping together, and the initial motion through space carries, even though it's on the other side of the planet. Like, if you jump up on one side of the planet that is moving away from, that is on the side of the planet where it's moving away in its travel, right? You would think that you would have a bit different gravity if it's motion based. There are ways to test this, and it would be interesting to find that out. It seems that gravity is so unchanging, that everything is holding together so nicely, that there is no literal difference between the gravity you experience on one side of the planet versus the other side. Relative, like one side versus the other side relative to its motion through the solar system or through the universe. The changes are so minuscule that you won't even if you do measurement, it won't actually make a like grand difference in the long scheme of things, although it could. Maybe, like if it's a fraction of a fraction of a fraction, once you multiply by a million, it could make some difference, because like spaceships take a lot in order to get out into space. So if you do that on the correct side of the planet, you might actually be doing it goodly. Which is why you probably don't want to be launching um, if the sun rises in the east and sets in the west, then you would, in other words, you want to be, wait, that doesn't actually say how we're moving through the solar system. I don't know. Um, yeah, I don't remember that. No, that has more to do. Well, no, it's relative to the sunset. You don't want to be launching at noon. Stop launching at noon. You're wasting power. Um, Although it might actually have other factors involved that make it so that launching at noon is the best thing to do. So the question is, should you be launching at sunrise or sunset? Not at midnight. Don't do that because now you're facing direct opposite of the sun. You're That's not the direction that the planet is moving. It's moving east to west or whatever. So that's how that works basically. At the moment of sunrise or sunset, you are facing this way to the sun instead of this way, where you actually see the sun facing right at you, right? Does that make sense? The orientation of the planet is that at noon, if you're going around the sun, right? At noon, you are facing the most towards the sun that you can. So if you were literally over there, you could launch and it would take more energy. If you're over there, you launch and it takes less energy. Does that make sense? It works a lot better with a three-dimensional diagram, but you understand. If you're launching from a rocket and you're going the same direction from the rocket, you don't want to be launching from the tip of the rocket. You want to be launching from the back because that'll get you away from the rocket a lot faster because it's moving away from you. You're moving away from it. They add up together. Versus if you're launched from the tip of the rocket, then they cancel each other out sort of because it's keeping up with your speed. Same difference, it's only a planet and it's rotating, so you got to figure that out. But you can do that, and it's a neat thing that they've done a bunch of work. They figured it out. Whatever. I don't care if it's working for them. Good, but I'm saying launch in the morning or launch at night. It's one of those. It all depends. For example, well, it doesn't matter where you are on the planet. No, it just matter. Well, it matters where you are on the planet. Yeah, it does. It matters if you're like your elevation in the planet. Like you don't want to be on the North Pole, right? We're off topic. It was microgravity, atomic gravity, particle gravity, molecular gravity. Which gravity are we talking about here? Anyway, so the thing about gravity, right, is, yeah, it's an emergent property from multiple objects all reacting to each other because of their motion through space. That's all. So protein folding is one thing, and it can lead to certain amounts of motion, but literally, um, like if you want to think about proper gravity, you think about an object versus another object. You think about like the atom versus the electron orbiting around it. And there was a theory talked about in this video where, um, which I don't need to explain more, that talks about the electrons all are identical. You know why that is, right? an electron cannot be made out of a different shape. The actual fundamental parts that make up the electron, you realize an electron is an item. It's not, I know that they said it's just probability. For their sake, it is. And I don't care. That's not reality. Reality is that the electron is a bar magnet. It's an extremely tiny one. Okay, it's on the order of magnitude that's like, it's slightly bigger than a photon, and it's definitely smaller than a proton, probably by the same ratio. I forget, it's similar to that. It's like if you were to think of the electron versus an atom, depending on the size of the atom, I mean, it's the difference between people and the planet, sort of, or something. There's ratios involved in there. The point is, you get to something this small, it's still made out of a thing. And this thing, okay, that it's made of, can only come in certain shapes. This specific shape is what makes the electron flow the electromagnetism through itself in the donut, the toroid that everyone understands about how magnetism flows through a bar magnet, around and back through again and around in that basic constant loop, right? And the electron, its field, you realize that field, the effect of the electron, is still stuff, right? Like the electromagnetic field isn't nothing. It's a thing. It's the base substance of the universe that's flowing. Electromagnetism is still a substance. It's just not physical in the way that, water would be physical, or the atoms and quarks would be physical, or the electron itself would be physical. The substance of the electromagnetic field is so absolutely tiny, and they're eventually going to figure this out, or they're just going to say it because it works with hydrodynamics and stuff. It works with fluid dynamics. Same kind of physics that apply to liquids apply to electromagnetism. So just think about it as the absolute fabric of the universe, thin stuff, the very small stuff. Now, when people talk about, so many times I hear people talk about the idea of a so many times I hear about people talk about the idea of multiple dimensions. What is the difference between really multiple dimensions and layers? The answer is there is none. Because you can have one type of radiation, right? And it's a certain type of thing, and its ability to go through objects makes it its own thing, existing separately, independently, maybe reacting, but for the most part, just there is that. And then if you look on another layer, you also find there's sand. If you look on another layer, there's water. If you look on another layer, there's light. like common electromagnetism, which is the radio waves and frequencies and all of that, happens separately from light. So, and independently, just flowing through each other. So all of these things all exist in the same cube, multiple dimensions. But it's not multiple dimensions in the way that we represent it in a four-dimensional cube idea. It's just the idea of having, for example, a color disk and another color disk on top of that. Only instead of on top of it, it's also like mixed simultaneously in the same space, basically. So you can't really tell the difference. Look, I heard all sorts of stuff on this video. A lot of it bothered me.
I bet most people would say would be the most mind-blowing science that anyone does. Wow. Because it's just it's out there.
Yeah.
You know, I could talk about stars and planets, and there's a tangibility to that.
Yeah.
Right? Even the size, even the expanding universe. It's a little weird, but it doesn't blow your mind.
Yeah.
You think about stuff that's like, what?
Yeah. One of my favorite experiences when I'm doing research is when I have a huge shift, when I'm shocked by something and I realize I've had some kind of preconceived notion that has just been shattered.
Right.
And it's really amazing. I'm following the science. I'm not dragging it
Right.
along.
Yeah.
Right.
And
One of those things is time dilation, unfortunately. It doesn't exist. In my mind, it does not. From what I understand about how time dilation works, it just doesn't exist as we know it. The main way that time dilation occurs is that your expectation of where the photons are relative to your expected, like, the distance of one object versus another object in the quantum, or I mean the atomic clock, for example. And I mentioned this a bunch. Almost all my videos, is that the atomic clock, it takes light, which is basically just a stream of photons, sends it towards the beryllium atom. It bounces off with a specific frequency. It comes back to the detector. And in the distance between the emitter and the beryllium atom and the detector, if that entire structure is moving through space, if it slows down at all, then there'll be like a Doppler shift of the amount of packets of light. Because light moves at a steady speed. It can only do that. There is no difference. It doesn't matter how fast you go, light will keep on traveling at the same rate. So if you send a bunch of light in any direction, if you travel in that direction, you're keeping up with the light and you're forcing it to go an extra distance. If you travel in the opposite direction, you're forcing the light to travel less distance. To the point where you can be going the opposite direction of the travel of light, and you actually make it so that light hits the collector. If you have the emitter here and the collector here, the instant that you turn on the emitter, the collector will have the light. Like femtoseconds is something that we have already achieved. But if you start moving, for example, at the speed of light and shine a direction towards the opposite way of your travel, you're going to end up having the light immediately hit the detector. There is no time between the I should say the amount of time that passes. Let's say it's 99.99999 with like a couple thousand nines the speed of light, and you send a pulse of light or any amount of light from the emitter to the detector, depending on the distance of the emitter and detector, right? So that if you're traveling this way and the light's going that way, it will pretty much be the smallest amount of time possible, and the light will already be at the detector. It'll be piling up there. But if you're going in the same direction as light, then the light will be piled up at the emitter in the back of the ship, and it'll never get to the front until you slow down. The moment that you slow down, then the light starts to actually be able to keep up with you. So if you're going faster than light will just keep on compressing. And if you're, in example, transparent, then the light will just be behind you all the time, like way back there. Hopefully you're transparent, because you don't want to be having any light be able to bump into you, because the moment it bumps into you, and more light bumps into you, it's basically like a laser beam. It'll just incinerate that particular atom. So if you have like a big enough source of light, like one of those big booming Hollywood signs that go boom, it shines the light, like the Batman signal, those things. Yeah, that'll base, if you face that opposite the direction of travel, start going in near the speed of light, you're going to be basically incinerating everything that the light could touch, which is a direct borehole through your ship. Not the smartest thing to do. Don't ever have lights on when you're traveling speed of light. It doesn't work nicely. Unless, of course, you're manipulating the light itself by using some kind of containment field, in which case, go ahead, because then you're changing the path of light and you're allowing it to be dragged along for the ride. So light will just be in pockets randomly. Yeah, as long as it's contained. Anywhere where it's not contained, there won't be any light. It will be pitch dark. You won't even be able to see that there is light out there. The light will be there, but as you understand, the only way that anything is illuminated is the photons bounce off of things and then hit you in the retina. So literally, if the photons aren't able to go anywhere, they're in patches. They're just these little balls of something that's out there. But until they literally aren't going to, there is no let's be clear, there is no actual light that's visible. It's not moving anywhere towards anything. It's just being stuck there. So it's darkness, no matter what. So the instant you go faster than light, you're going to have complete darkness. It's not that the light is going to all pile up in one spot and you'll be able to see that. It's literally going to just be there, and it'll be darkness. There is nothing you can see in behind you. The only stuff you can see is stuff in front of you. and it'll be whizzing by really fast. Stuff at the distance will be easily noticeable. Hopefully you'll stop in time, especially if you time it correctly, then you'll actually be able to do it nicely. But otherwise, like, it's a blur. It's just like Star Wars. You warp through time, light just passes straight by you, like whoosh. You know, it does that. That's reality. That's not even science fiction. The phenomenon of that is reality. If you were able to actually do it. That's how it works. That's what it do. That's how the experience would be. But like there is no light behind you. You're not illuminated. It's pitch black. It is pitch black. So what else happens? Are electrons and the rest of the parts of the molecular stuff in the body able to do anything with, like, would they just be stripped away and everything? And that's an interesting question. Particles accelerating to the speed of light and whatever else, or being pushed to the speed of light by some kind of carrier wave, can be affected by physical processes. So they themselves, as like a block of metal, can possibly survive going the speed of light, no problem, depending on the carrier wave that's pushing them. And if anything is piling up, hitting it, that's one thing, but who cares what you're moving through as long as everything is deflected. Like the whole reason why the Cuvier drive is thought as being possible is because it moves everything else out of the way. You don't bump into anything. You're just having everything move around you. And so really the best way to do it is to shine a laser really far into the distance. And then the distance that laser has been able to go, that's where you're able to push everything else out of the way, because the light's in that path, technically. But still the light is moving at light speed. Lasers, however, are not regular photons of light. They are accelerated. Right? Or are they just released? Like, is a laser not something of a physical nature that has more oomph to it than actual regular photons? Or is a laser just a diode and magnification? You know? Like, once you start pushing things, like the light itself can't move faster than light. It only has so much energy to be able to do anything. It's not an engine. It can't give extra oomph. But if you can make an engine with extra oomph, then you can go faster than light. There's no reason you can't. The question is, can you survive? Can you have your ship not disintegrate? That's the only question. It's not the fact that you can't, it's that you probably shouldn't, or that it's not likely that you'd make it, even if you are a hunk of metal, or whatever. Surrounded by electromagnetic fields, or whatever. Even if there's nothing in front of you. Well, that's an interesting thing. What could survive the speed of light? Ironically, we know that it takes less energy to separate quarks, and that's the strong force, and that's the strongest amount of force that we know. But there is a way to separate quarks. The only thing is, the moment you separate them, they turn into another two pair of quarks. Each individual makes its own extra. So the one on top is now, the A is now A2 and A1. The B is now B2 and B1. They used to be AB, now they're that. And that's how that works. So even them would be separated by these things. Is there any force at all that could handle the traveling of the speed of light? And the answer is no. So we have to avoid physically traveling through this at any speed near the speed of light at some point, because we just get, as they say, spaghettified. Mostly because individual parts don't want to just bump into each other. Some parts will lag behind, and other parts will be bouncing off forward and stuff. It's interesting to think about how helium balloons work and how you can have the helium balloon be full of stuff and it all bounces off of each other in the balloon. And as it bounces, its energy, its momentum, forces other oxygen out of the way. So much pressure in it, but so little stuff that it just, all the other stuff is pushing down, and the balloon is technically, it's not so much that it lifts up, it doesn't have anti-gravity properties, but instead everything else decides that it is heavier, it flows to the bottom. And the balloon is like the cream that goes to the top. That's how helium balloons really work. That's how buoyancy works. Lighter stuff floats because everything else pushes it down, and there's no real way for it to resist. It will just go up. So, interestingly enough, so if you have like the heated air and the hot air balloon, the hot air is a lot more bouncy, a lot more light than the air around it. So all the other air is heavier than the balloon. Atmosphere is heavier than the hot air balloon. So it pushes down. All the rest of it just seeps down under the balloon and lifts it up. It's not that the balloon lifts up at all. It's that everything else pushes down more than the balloon lifts up. Then the balloon pushes down. That's how that works. So the moment you understand that, the moment you start being able to build a space elevator, because all you need are these types of hot air balloon type things to hold up the structure, so that you don't have to have everything weighing on top of itself. Regular buildings need this, but the space elevator is not going to need structure underneath it. It will have the atmosphere, and it will be sitting on the atmosphere. Every section will be held up by giant balloons that hold it up. And it doesn't matter how, it literally, the bigger you go, the better, because the more atmosphere you're holding up. So it has to be made in sections, like a spine. And so the space elevator of the future will be a spine, the main core structure, right? And then outside will be these balloons, and the atmosphere will hold everything up, because the atmosphere is heavier than the balloons. And the balloons pull the thing up. So the question is, how do you make a structure like that in a big form? Like, making Zeppelins, not too incredibly difficult, and basically all you need is Zeppelins. And you just need, like, what, 100 Zeppelins? And we have those Airbuses out there. So if you have like 100 or 1,000 of those, and the structure of the stuff that goes between each balloon so that they're all tethered within each other, like the only thing that's not held up by the balloons itself is the tether and the weight of the stuff as it's being held by the tether. So understanding the primary function of how elevators normally work in a very tall building, you can have sections that are held up by the balloons powerful enough that they can self-sustain where they are. You can have like propellers and ion drives that can push stuff around so that they stay relative positioning. Like, don't put this thing in Hurricane Valley, but I mean, find somewhere nice and calm and put it there, and there you go. That's how it'll work. It can't be a solid structure, right? And even if it is a solid enough structure, it's still going to be held up by air. It's not going to be held up by cement. It's going to be held up by air. And if you think holding up by air is less crazy than holding it up by cement, understand that cement compresses with a lot of force. And it only takes, like Burj Khalifa, we've gone to the limit of tall structures that aren't held up by the atmosphere. The moment you start holding up, like, if you understand how the air balloons are able to hold up like a few people, and the balloons are massive, right? Then you understand that in order to hold the kilograms of material that you want to put out into space, you need gigantic balloons the size of Marvel movie, what is it? Those Zeppelins, those air carriers. Those are the ones that you need to be able to make space elevators work. You need something that big. Only it's not going to be just big. It's also going to be floating. It's also going to be the density and using the buoyancy force. That's all you need. Interesting fact, you don't even have to have, like, they have these giant balloons that are filled with helium and whatever else. They can hold up a single person and it's inside of someone's barn. And that's fun. And then just the leaks of how the gas pulls out of this makes it so you have to constantly maintain the gas pressure in that balloon. You can't make a perfect seal. The stuff just ekes out because of the chemical composition, the size of it compared to the seal. You can't make something with a seal tight enough to hold the stuff. It will just eke out. So, and multiply the square meters of volume of mass. Every square meter of surface area has a potential for eking out this gas because it's so thin, because it's so tiny. So the only way to make it better is to make a mesh that's tighter, knit together, so tight that even the tiniest of atoms can't just slip through it due to pressure. There's only so much you can do to hold helium in. Like, it's going to just pass right through it. Almost similar to quantum tunneling. Exactly the same as quantum tunneling. It's just like moving through Swiss cheese. You can do it. The holes are there. It's not like it's a solid wall. It's Swiss cheese. So if you can find the holes and you're small enough, you can just pass right through that. The only thing that's stopping you mainly is the electromagnetic fields around with the electrons. In other words, stop using carbon. Start using heavier stuff. You know, you really want to hold stuff. You don't want to use carbon. You want to use something with a much bigger atom to begin with, that all the electrons are able to also somehow be in this lattice. Like metals have a better ability to hold in gas than any amount of carbon fiber. And diamonds. Yeah, diamonds eke out stuff worse than metal. Because the thing about metal is that metal is denser, there are more electrons, the bubbles of the electrons are bigger, and the same function that works with quantum tunneling is the same function that allows, at pressure, helium to escape, because it can go through those bumps. Even though there's electromagnetic field bubbles around the electrons that takes up the space of those gaps, and that's why those gaps exist in the first place. Like if you can make matter like an actual solid, like actually solid matter, you wouldn't be using atoms. Think of an atom, but the entire proton-neutron mesh is a sheet of proton-neutron. Eh? Then instead of a ball of proton neutrons, why not have a sheet of proton neutrons? Why does that not work? Equilibrium. It doesn't want to take that shape. But if you could find a way to do that, make a sheet of proton neutrons instead of a ball, and use those balls in a chain link fence, just use a sheet of proton neutrons. Then helium won't get through. That's how you have levitation. That's how you have the ability to not worry about the helium popping out. But we're talking about an atom that is now bigger than uranium. It don't like to form that big. And it certainly doesn't like to form sheets. It likes bubbles. It really likes bubbles. You would have to redesign the atom to make a sheet of proton neutrons. Okay? You can't just do that. That's not something people, for theoretical physicists, you probably have thought about this already. Just make a sheet of bubbles. But, I mean, proton neutrons. But, how? You know? That's the real thing. That's the secret, though. That's the material of the future. That's going to be fun. I look forward to it. But also how? You know? And no one talks about this idea of making a sheet of the proton neutrons, because you can't. It'll just break down. It usually just breaks down. Because at some point, like, it just wants to separate into two smaller atoms. That's what they do. It'll just fission off. It won't actually create that structure. Is there any physical way for you to make this work? The answer is probably no. Probably no. There was pressure in my bottle. You know why? It was cold and then it got hot. It got warmer and the stuff inside, especially the air, expanded. Mostly the air. So it made a little pop when you open it. And if you don't want it to pop, cool it down first. That's an interesting thing. But anyhow, yeah, I gotta make a separate video just of that. Make a sheet of proton neutrons. Holy crap, it's not gonna happen. It's just not. The way that they interact, the way that everything forms, the way it likes to make balls instead of anything else. Like, if you could make a sheet of the stuff, how would you even do it? Like, it would just be solid matter at that point. And all you really need is, like, what? To squish down a uranium, you would have a sheet, like the same amount of proton neutrons. You would have a sheet that's like 5 wide or something. Like it's what, 40, 400 or 40 or something? What is it? What's the number? Is it 40? I don't know. Anyway, 40. Oh my god. Give me a second. And that's why you pause the damn live stream before you start working on the uranium-235. Yeah, that's what I thought. It was 92. I said 40. What the hell is wrong with me? Okay, whatever. You get the idea, though. So, if you squash a uranium atom, like 25 is a better number to work with. Then you have a 5 by 5 grid, right? But you want twice that. So uranium's actually not that bad. It's near 4 times that. So you would have it like almost 4 times thick. Or if it's 3 times thick, three of them, right? But it's a sheet of 3 proton neutron. That's stable enough. And then you would have, well, I mean, bowling ball packing, you know. But I mean, you would be able to have like, what is it, 30? No, that's not how. A 5 by 6. 5 by 6 free wide. Where the fuck am I going? I'm getting a drink. Where's the drink? It's this crap. What is this? It's Sea Boost. I don't know what Sea Boost is. It's got pears in it. I don't know. Anyway. A bit of Sea Boost, a bit of Strawberry Passion awkwardness. Awaken it? Award? What the fuck? That's too much. That's not too much, actually. I forget that I need to leave the water out until last and try to fill it up and then add water. That's what I need to do. Milk. People think you don't actually drink that, and I'm like, I drink that every day. This is what I drink every day. This weird concoction of, like, it looks like that's actually like colored. There's color in there. It's yellowish. What the fuck is on? I don't know what that was, but it's just clean the stuff that was floating in my cup or whatever the fuck it was. I don't know what the fuck it is. Stop looking down for a second before you look at feet. My feet are covered in socks. What are you talking about? No, not that water. Okay, whatever. It's fine. I have my drink. Okay. Sheet atoms. Can you do it? Um, I would say you probably can't, right? Am I right? You probably can't do it because if you could do sheet atoms, why don't we find them? You know? The reason why it takes that shape is because of how things be, you know? I mean, what's the difference between a sheet atom and like carbon nanotubes or whatever? The answer is there's holes between them. Literally. Giant holes the size of the difference between the distance between electrons and the atoms. It's like there's an atom, there's an electron, and then there's another atom, 3 parts. They're all separated by electromagnetism. And there's that space difference, the thing that makes it impossible for the stuff. But I'm talking about solid matter, sheets. Like once you start pushing stuff closer and closer together, you usually end up with just clumps and fusion. The reason why a lot of stuff wanted to turn into whatever is because when it got super hot, it fused together. That's why you end up having regular matter be able to form heavier and heavier objects. The beginning of the universe made carbon. It made hydrogen. It made heavier objects. The initial ignition event. And these giant clumps of, these tiny little clumps of what was the proton-neutron stuff makes the atoms, right? The atoms then make, what the fuck? What do you mean I sent something? Okay. When the protons and neutrons started, right? And the antiprotons and the antineutrons started, all that the antineutrons could do was make helium. So the instant that it blew up, it fused together with whatever other existed. But when the regular matter blows up, it normally compresses and makes carbon or makes oxygen. It makes denser stuff, helium or whatever. So you don't end up with item 1 on the periodic table. You end up with 2. Like, come on. The instant that you do that, now instead of everything taking this uniform space, that stuff takes up less space, making gaps, making vacuums, making motion. So that motion then makes the swirling and the compression that makes stars start to form, that makes the gases, that makes Jupiter, and makes all the other things compress and do its thing. Right? That's the first stage of everything, is that it started off as proton neutrons. It collapsed into regular, like the strong nuclear force, like starts activating, right? But what is this strong and weak nuclear force? Well, there's these gluons that pass between the different quarks. So they fuse together to make proton neutrons. They clump together to make atoms. Like the reasons, I it's interesting to think about why neutrons clump together with protons, but it's basically that the neutrons only have so much energy in and of themselves, and they still want to flow that energy, so the protons are glad to do some stuff with that. So they all bind together, making the atoms. Interesting that you have these residue electrons just out there. Like, would proton and neutrons still be a thing if electrons weren't there? And the answer is probably yes. Like, you strip the proton neutrons of all the electrons. Like, if you strip uranium of all of its electrons, would it still be uranium? And the answer is probably yes. I mean, there are people out there who have these definitive answers, but the point is, you end up with the positive on the outside, the negative on the inside, and basically all that can happen, especially if there was antimatter in the beginning of the universe, whatever stuff, then you have a bunch of negative stuff, or a bunch of stuff that flows electromagnetism in one direction. And then you have the positive parts, the positrons and the antineutrinos or whatever, the protons and the neutrons, all of these parts. All that happens is each interaction between all the different possible stuff makes for different clumps. The clumps all organize things until they're basically uniform as much as they can be, and they keep on going and they make planets and stuff. I mean, really, how can you say that there's no such thing as a theory of quantum gravity if you don't, like, literally what is the strong nuclear force? As long as you can understand that, you understand quantum gravity. Like, what are we even talking about here? What are we asking? What's missing? You know, you already have the parts of what makes things do things, don't you? Like quantum gravity, proper gravity, um, is just motion and stuff bumping into each other, not allowing the rest of it, and the momentum of it is enough that it keeps on moving, even though it's on the other side, because it all moves through space in the same speed, even if it's swirling, right? Anyway, that's enough for this science talk. I'll see you in the